Hey everyone, so we all know the average, right? It's that one number we always use to sum things up. But what if I told you the average is usually hiding the most interesting part of the story? Today, we're going to pull back that curtain and look at a tool that shows us the whole picture: standard deviation. So here's our game plan. First, we're going to see why the average just isn't enough on its own. Then we'll meet our hero for today, standard deviation. We'll peek under the hood to see how it works, unlock its superpower with something called the bell curve, and then, finally, we'll learn how to see where any single piece of data fits into the crowd. You know, we use averages for literally everything. Average weather, average salary, average test scores. But as you're about to see, just relying on that one number can actually be a real trap. Okay, check this out. We've got two basketball teams, Team A and Team B. Now, look at their scores. Both teams have an average score of exactly 12 points per player. So based on the average alone, you'd think they're basically the same, right? But would you bet on them the same way? Yeah, probably not. And here's why. Team A is super consistent. All their players score right around that 12-point average. They're predictable. But Team B, they are all over the place. You got one player with a really low score and another with a super high score. They're totally unpredictable. See, the average score of 12 completely misses that huge story about consistency versus chaos. So that kind of begs the question, doesn't it? If we want to understand the spread, the consistency of the data, what tool do we even use? And here it is. This is our answer. Let's meet the hero of our story, standard deviation. It's the tool that was literally designed to measure that spread and tell the story that the average just can't. Okay, now I know the official definition sounds a little intense. The square root of the average of the squared distances of the observations from the mean. Let's be real, that is a mouthful. But the actual idea behind it is surprisingly simple. So let's just break it down to this. Standard deviation is basically one number that tells you the typical distance any data point is from the average. That's it. A small standard deviation means all the data is clustered together, like our consistent Team A. And a big one, it means that data is spread way out, like our unpredictable Team B. So how do we actually calculate this typical distance? Come on, let's take a quick look under the hood. Don't worry, we're not going to get lost in a bunch of crazy formulas. But you'll totally get the simple logic behind it. It really just boils down to 3 steps. First, you need a starting point, right? So you find the center, the mean. Step 2, you look at every single data point and measure how far away it is from that mean. And finally, you find a special kind of average of all those distances, and boom, that gives you the typical spread, the standard deviation. Now, you might be thinking, what's this special average thing? Well, some of your data points will be below the average, so their distances will be negative. And you can't just average positive and negative numbers, they'd cancel out. So here's the clever trick. We square all the distances to make them positive. Then we average those squared numbers, and at the very end, we take the square root to undo the squaring. That gets us back to our original units and gives us our answer. This table shows it perfectly. Let's say our data is just 3 numbers, 5, 10, and 15. The average, or mean, is 10. The distance, or deviation for 5, is -5. The deviation for 15 is +5. But when we square them, they both become 25. See? It treats their distance from the center as equally important. From there, we can find our special average. Okay, so we can measure spread. That's pretty cool, but this is where standard deviation goes from being just a measurement to having a real superpower, especially when we see how it works with one of the most common patterns in all of nature. So it turns out that in the real world, we're talking everything from people's heights to test scores to tiny measurement errors. Data loves to arrange itself in this beautiful symmetrical shape. We call it a bell curve. In standard deviation, it's the magic key that lets us read this map. And here's the first secret the map tells us. About 68% of all your data, so most of the normal everyday stuff, is going to fall within just one standard deviation of the average. So if the average test score is an 80 and the standard deviation is 5, that means about 68% of the class scored somewhere between a 75 and an 85. Now let's go a little wider. If we go out to 2 standard deviations from the average, we capture a whole lot more. About 95% of all the data will be in this range. For our test scores, that means pretty much everyone, 95% of the students, scored between a 70 and a 90. And if we take one more step out to 3 standard deviations, we've now included over 99% of everybody. Anything that falls outside of this range is incredibly rare. We're talking about a true outlier. This whole thing is called the 68-95-99 rule, and it is so powerful. It basically turns standard deviation from just a description into a predictive tool. It gives us this amazing framework to instantly tell what's common and what's exceptional in almost any situation. But what about just a single data point? How can we tell if one person's score is really good or just kind of average for that group? Well, standard deviation has a tool for that too. It's called the standard score, or you'll often hear it called a z-score. It's a super useful number that tells you exactly how many standard deviations away from the mean your specific data point is. And the formula to figure it out is so simple. You just take your observation, subtract the mean, and then divide the whole thing by the standard deviation. That is it. Let's use an example. Imagine a purity test for some chemical. The average impurity is 0.166%, and the standard deviation is 0.058%. You test your new sample and find its impurity is only 0.108%. When we plug that into our simple formula, we get a standard score of -1. What does that tell us? It means your sample is exactly one standard deviation less impure, or in this case, better than the average. You can think of the standard score as a kind of universal translator. It can take any data point, a score on a test, a person's height, whatever, and it translates it into a universal language of how typical is this thing. A score of +2 is always really high, and a score of -2 is always really low, no matter what it is you're actually measuring. It gives you instant context. So in the end, yeah, the average tells you the center of your data, but it's the standard deviation that tells you the story. It shows you the consistency, the predictability, and it draws a line between what's normal and what's exceptional. So the next time you see an average, just ask yourself, okay, but what's the spread? And what's the story that it's really trying to tell me?